Hello and welcome to Snax. Today's presentation is fitting a model to stability data per ICH Q1E. Today's presenter is Laura Pack, Senior Director of QC and Statistics at Resolute. Laura, the floor is yours.
Thank you. Today's presentation is fitting a model to stability data per ICH Q1E. Today's Stats Snack will show you how to fit a model to a stability dataset containing more than one lot using a fixed lot model as prescribed by ICH Q1E. Today you will learn how to account for batch-related terms, also known as lot-related terms, when the stability dataset contains more than one lot. You'll also understand the practical implications of the analysis results. Recall from a previous Stats Snack that the purpose of a stability analysis is to predict the mean response for a lot over time to estimate a retest or expiry period. The equation for the line of best fit is relatively simple if the trend is linear and there's only one lot in the dataset. We can think of it as y equals mx plus b plus some error, which for stability data translates into the slope times time plus the intercept plus some error. This plot shows stability data for lot A and a fitted regression line, which represents the predicted mean for the individual points. When there is more than one lot in the dataset, we need to consider a more complex model. Early in development, when there are few lots on stability and relatively little prior knowledge about the degradation profile, the model detailed by ICH Q1E is used to evaluate poolability of individual regression lines. When Q1E describes the need to evaluate poolability, the question at hand is whether one line can estimate the trend for all lots in the dataset. Scientifically, we must consider that different lots may start at a different value or may change in a different way over time. Statistically, we can examine whether these differences are significant. Analysis of covariance, or ANCOVA, is used to conduct hypothesis tests to evaluate similarity of the lot's slopes and intercepts in a stepwise fashion. Per ICH Q1E, we use a significance level of 0.25 to test batch-related terms, which means that the p-values for the lot and lot by time terms from the model are compared to alpha of 0.25 to determine the outcome of the hypothesis tests. First, the full model is fit, which is a model that allows for different slopes and different intercepts for each lot. That's the model we looked at before. That's y equals some intercept plus lot times time. A hypothesis test of the lot times time term is conducted to ask, is there evidence that the difference in slopes is greater than 0? The p-value for this test is compared to 0.25, and a p-value less than 0.25 is taken as evidence that the lines are not parallel. In this case, model reduction stops, and we use the separate slopes model, where each lot is fit with a separate regression line. Each lot has its own slope and intercept. However, if after fitting the full model, the p-value for the lot times time term is greater than 0.25, there is no evidence that the slopes are different. We then examine the intercept term to ask a similar question. Is there evidence that the difference in intercepts is greater than 0? Now, the p-value for the test of the lot term is compared to an alpha of 0.25, and a p-value less than 0.25 is taken as evidence that the intercepts are not similar. In this case, model reduction stops here, and we use the separate intercepts model, where each lot is still fit with a separate regression line, but each line is parallel and differs only in the value of its intercept. If both hypothesis tests return results of no evidence of a difference, in other words, the p-values for both batch-related terms are greater than 0.25, then we consider the lots poolable and fit a common regression line. This means that statistically, one line is sufficient to predict the mean for all the lots in the dataset. So in the end, 3 models are possible, depending on the outcome of the stepwise model reduction based on hypothesis testing of the batch-related terms using alpha of 0.25. There is no model that fits separate slopes with a common intercept because the lot term should be retained if the lot times time term remains in the model. Note that per ICH Q1E, other methods for estimating shelf life are acceptable, and those will be discussed in a later stats snack. For today, let's continue with this paradigm, also known as the fixed lot model, by looking at a few examples. As we just discussed, the model is based on the outcome of hypothesis tests on batch-related terms or lot-related terms. This table shows p-values from the full model fit to these three lots with individual regression lines shown in the figure here. We begin by looking at the p-value for the lot times time term to ask whether there's evidence that the difference in slopes is greater than 0. In this case, the p-value for lot by time is 0.0283, which is less than 0.25. Therefore, we conclude that there is evidence that the lines are not parallel and model reduction stops here. Expiry will be determined using the full model or separate slopes model. Per Q1E, the lot with the shortest estimated shelf life sets the shelf life for all batches. I'm going to call this lot the worst case lot. So how do we determine the worst case lot? Typically, in the separate slopes model, the lot with the most extreme slope is the worst case lot. However, we still need to calculate the confidence bounds on each lot because it's the intersection of the confidence bound and the specification that sets the shelf life. In this example, lot C is the worst case lot because its confidence bound intersects the specification soonest out of the three lots. This plot shows the appropriate way to represent the regression line that sets the shelf life based on lot C, the worst case lot. Using this analysis, a 24-month expiry is supported with up to a maximum of 26 months. Note a few things about this analysis. The separate intercepts model still has a worst case lot since each lot has its own intercept and one line is presumably closer to the specification, even if the lines are parallel. Also, this analysis uses the predicted mean for lot C. So it is possible to observe an individual out of specification result prior to 26 months. To determine the risk of an OOS prior to expiry, a different analysis is used, calculating a tolerance interval, which will be covered in a different stats. Let's review another example where we can reduce the model beyond the full model. Based on this statistical output, the p-value for lot by time is 0.5850, which is greater than 0.25, so there is no evidence that the slopes are different, and we remove the lot by time term from the model and refit with a common slope but different intercepts. This is the model output for the separate intercepts model and the fitted regression lines from it. Notice a few things. As we expect, the lines are parallel but have different intercepts. Also, the p-values for the remaining terms have changed slightly, but the overall conclusions about the terms have not changed. There is still no evidence that there is a difference in intercepts because the p-value for the lot term is 0.6520, which is greater than 0.25. The overall conclusion from this model fit is that one line is sufficient to describe the trend for these three lots. We can remove the lot term and refit the pooled model. This is the output for the pooled model with one regression line for all three lots and no batch-related terms. Per ICH Q1E, non-batch related terms are evaluated at a significance level of 0.05. Notice that the p-value for time is 0.2957, which is greater than 0.05, so there is no evidence that the change over time is significant. However, we typically retain the time term in the stability model for the purpose of estimating shelf life. This is the final plot used to represent the shelf life model for this attribute. Based on the model, a 24-month shelf life is supported. Further, since the change over time is not statistically significant, we can say that this attribute, potency, is not shelf life limiting. That concludes today's stats snack on fitting a model to stability data per ICH Q1E. For further information on the concepts discussed in this video, refer to the guidance in ICH Q1E, and please contact me or pose questions online to the AAPS CMC Statistics community. Thanks for joining us today for Stats Snacks. Please connect with us on the AAPS CMC Statistics community and look for more Snax videos coming soon.